true sign of intelligence is not knowledge, but imagination. Albert Einstein. Hello and welcome to the bioprinting session powered by Altem, hosted by Biotechnika. I'm your host Shekhar, and today is the 6th session where we come to you live to discuss one of the most unique topic of today, which is high resolution bioprinting with hydrogel photoinks. Today's session is nothing but imagination. Once upon a time, all this was just imagination, but somebody made it reality. And that's what amazes me. That's what is something which you should take away, apart from, of course, all the knowledge which our speakers are going to give today. And that is, imagination is the true power of researcher. If you want to become a great researcher like Edison, like Einstein, then you have to be imaginative. And today's session, we are going to talk about one such future concept which is becoming a reality today, and that is using hydrogel photoinks to reproduce high-resolution bioprinting. So people, this is going to be a power-packed session, and I invite you to attend this session. Today is the 6th session, the last session of Altem powered webinar on bioprinting. And we have requested for one additional session probably for the Q&A. But if we are not yet confirmed on that. So ideally, this is going to be the 6th session. And after that, we'll be releasing the e-certificates to all those who have attended all the 6 sessions. Now, to start with, if I have to, recall when we started the first session of bioprinting in May, late May, I saw the enthusiasm in most of you. And what amazes me, what makes me happy today is I still see that enthusiasm in all of you, that enthusiasm to learn and that enthusiasm to become a great researcher. So I'm sure all of you have already shared this video link, this webinar link with all your friends and colleagues. Have you done that? Yes? Okay, wonderful. So today's session is going to be super special because we have our speaker with a lot of experience in this topic. And this Altem powered 6 power packed sessions which we conducted, and today is the 6th session. I want to remind you that throughout the internet and throughout the globe, this is the most valuable insight you could get from an industry expert right inside bioprinting. So this is really, really exclusive information which you got in the last 5 sessions and of course in today's session. And the videos are always going to be there on Biotechnika's YouTube channel. Please do refer them, share with your friends and colleagues. And of course, whenever you are doing some kind of research where you want to implement bioprinting technology, then you know whom to approach. You know Altem's website, right? You have to go there and talk to them. They are the experts in bioprinting, 3D bioprinting. So now, before I pass on the controls to our speaker of the day, I have only one request for all of you. Please attend this session till the end, because we are going to distribute the e-certificates based on this session also. Once you have filled all the forms at the end, then only you are going to get the e-certificates. Apart from that, please make sure that you are entering your correct email ID and phone numbers, so that if in case Altem wants to contact you or you want to contact Altem, you will be in touch with them. Also, there is a contest going on LinkedIn profile of Altem. Please go ahead and participate in that. I saw a lot of you participating, right? So please do that. And they're going to give away the Amazon vouchers to the winners. And yes, like we have promised, we are going to give the 5 most active participants throughout the 6 sessions Biotechnika t-shirts. Okay. So without taking much of your time, it's time to invite our speakers. Over to you.
Hi everyone. Good evening again, and thank you for joining me on this session, which is the sixth session of our series. And the topic is high resolution printing with hydrogel photoinks. I am Aishwarya Shirur, and I'm a technical specialist at Altem Technologies. So, while we proceed with the rest of our session or the main crux of this session, I'll just go back to telling you about all of the applications just as a reminder. And from there, we'll be able to exactly understand the use of what high resolution printing or high resolution bioprinting is. So, we started with an introduction to 3D bioprinting, followed by what is the application in tissue engineering, soft robotics, and organ on a chip was one of the areas. Then we worked into drug discovery, drug delivery, and now we are coming into this entire section, which is high resolution. So, this image that you see to your right is actually an image of a vascular lung structure. And in fact, this is a perfusible, rather a breathable lung. And this create quite a lot of tension or quite a lot of fascination in the field of tissue engineering itself, understanding that this was vascular. What you see red around this is actually the flow of blood, or rather an imitation of blood. And you would see that there is a amount of air which flows into that sac, which makes it bulge up and then expand, basically expand and contract. So the idea of printing this is what we're going to talk about, and I hope this makes things clear for you as I proceed with the session. And as usual, I'm going to begin with talking about us. And so we are Altem Technologies. We're a 3D innovation platform company, and we work with several industries, and we work with several products. Starting with Dassault systems for CATIA, MSc software for computational fluid dynamics or any sort of other simulations. We have Stratasys for plastic printing. All three FDM, PolyJet, SLA prints. Then we have Artec 3D for the 3D scanners. Then we have Dassault systems again for BioVia. This is for in silico modeling or life science simulations. And then we come to CELLINK, which is 3D bioprinting. And it's been a couple of years where we started from 2011, and now we are still growing, and we are still adding on the list of people to our customers and partners. And while our customers are in the area of education and research, aero defense, automotive, healthcare, IT solutions, customer products, and it keeps growing, right? So life science and healthcare and every other industries where we are always working and still helping out with. So while we come to the main part, I will again give you a brief about what 3D bioprinting is for the people who did not join the previous sessions, and give you a quick recap. 3D bioprinting is a form of additive manufacturing. Like we all know, where you use cells, you use biocompatible materials, which are called bioinks, and then this actually creates your model layer by layer in order to mimic the behavior of natural living systems. So, 3D printing, 3D bioprinting is actually derived from the idea of tissue engineering along with 3D printing. And the main components here are cells, bioinks, and the culture media. So I'll play this video for you. So this gives you a quick recap.
3D Bioprinting by 𝗕𝗓𝗏 with the Nguyen Lab at UNC Chapel Hill. We print things all the time. Whether they're documents, posters, or flyers, printing is an important technology in our daily lives. Relatively recently, however, printing took a big step forward with 3D printing. We could build a 3D model on the computer, send it to the printer, and we could have that object in our hands in hardly any time. What if I told you that this isn't the limit? There is more to explore. What if we could print living things made up of cells? We could make blood vessels, tissues, and organs. We could help the hundreds of thousands of people waiting on transplant lists. This idea is not too far from reality if we use 3D bioprinting. 3D bioprinting is just like normal 3D printing, except it uses living cells as ink to create living structures. Like 3D printing, you have to create a model on a computer, then layer by layer, your living structure will be printed. The first step in the process is known as pre-bioprinting. Here, the desired product is determined and studied. Oftentimes, 3D scans, such as CT scans or MRI images, are taken of the desired product and are then converted into a series of 2D images to serve as a template for the different layers. Cells are then isolated and extracted from an organism, which is often the recipient of the product, in order to create bioink. Bioink is one of the most important parts of the 3D bioprinting process. It starts with the cells that were extracted. Then, molecules called hydrogels are added to provide water for the cells. Other nutrients and chemicals are added so that the cells can grow and communicate as if they were in a living body. Once the bioink is developed, we reach the step of doing the actual printing. Using the bioink, our organ is printed layer by layer until we achieve our final product. There's not just one method of bioprinting. Different types include inkjet printing, acoustic printing, and laser printing. The most common type of bioprinting, however, is extrusion printing. This method is probably how you would normally think of 3D printing. The bioink is loaded into a printing chamber and is pushed out a round nozzle. The nozzle produces a tiny filament that is often around 400 microns in diameter, or about the thickness of 4 pieces of paper. Once you've finished the physical bioprinting portion, the final step is solidification. In general, bioink is a viscous liquid, so in order for it to become the desired product, it needs to harden. Sometimes the bioink will solidify on its own. Other times, the process of cross-linking will occur with the aid of things like exposure to UV light, physical changes like heating or cooling, or chemical changes due to the addition of certain compounds.
So this gave us a quick recap. And now we'll come down to the types of bioprinters. So I have already mentioned this in prior, but this will give you some perspective with what direction we're reading into. We have looked into inkjet bioprinting, laser-assisted extrusion, and stereolithography. Over the last couple of sessions, we have continuously spoken about extrusion printing with our set of bioprinters. And we know that extrusion printing is basically using either mechanical or pressure or indirect pressure to extrude a filament, right? Now, similarly, when you talk about a difference in technology, we come into a section which is stereolithography. So stereolithography is actually a light assisted method, and this light is what is going to drive the formation of the layers which you want to create. So I'll explain as we go. Stereolithography is a photopolymerization based method. So photopolymerization means the chain of the polymers will come together or interact together or cross-link when there is light applied, right? So this is a rapid prototyping technique, and here you have computer data, which is the CAD models which are used, and this will spatially control the radiation of liquid resin. So when you talk about SLA, you have a vat, basically a plate consisting of a resin of your choice, and to that resin you will have the laser which falls onto it. So as this laser falls over this ink, with each time the resin actually cures. Basically it solidifies. So in this process where you're talking about polymerization or rather curing, the ink, which is ink or the hydrogel or the resin, which is probably in the liquid form, the fluidic form, is going to convert into semi-solid or rather solid. So this is the idea behind SLA printing. Now, why SLA printing is considered better, how are we progressing towards it, is because it actually enables structures with precision. So you can develop or create structures in the micro scales, and this is for better resolution and for better structures. So here I'm giving you an example of an SLA print. This is a general SLA print. But when you look at the complexity of the image, you will understand that for it to stay mechanically stable and to create those mesh-like structures in the middle is quite an effort, because we need to have the stability, we need the shape fidelity, and we need other factors to also play in when you're creating this. So this is an example of a general printed plastic SLA structure. Now, when we go to something which is more relevant to bioprinting, since this session is on bioprinting, I will talk about DLP printing. So DLP printing is considered to be a sister technology to SLA. It's called digital light processing, right? So here the light is going to be processing the resin material. So here obviously it is going to be light assisted, it is filament independent, it is of high resolution, and it creates watertight models. And there are maybe limited set of materials which are available. So when you talk about DLP versus SLA, it's actually million pixels of light which are falling on the resin bed instead of just one focused laser beam, right? So that's the difference. That's why this is also considered a little more accurate, because you have many pixels creating precision in the design that you create. So we know that there is a liquid resin which we are using, and the liquid resin stays within a vat. You have a built platform, and then you have the light source which is going to help in it. So I'll tell you about the working principle now. So when you talk about DLP printing, we said we are going to be using light. So here we have 405 nanometers of industrial projectors. So the light, or the intensity or resolution of the light, is going to be 1280 by 800 pixels, right? So this is now projected onto these DMDs, which are micro mirrors, which are within a encapsulated set. This reflects the light, takes it to the top, which is the PDMS lined vat. There is maybe a droplet of the resin that you have. Then simultaneously, as the build platform moves, it goes on printing, right? So this goes on projecting a series of images in order to create that layer, that structure that you want. And when you go to the steps, it goes from design 3D models, which we generally go with maybe CAD models. Then we go through a process of slicing that CAD model. Basically, you have something complex, you try to simplify it, and then create that same structure again, right? So this layer, which is, or the set of layers that are sliced, right, they start to stack up together to form your entire object, or the entire model that you want to create. So this projected pattern light, as you see here in the bottom, you see this blue light which is falling. This projected light keeps on changing each time. It keeps blinking. There is an on, there is an off, there is a movement of the build platform as the structure is being formed. And eventually you will have a printed structure, right? So this printed structure will definitely be more watertight. It will have less amount of spaces between it. You can obviously modulate the porosity based on other set of studies. So I show you this more in detail so that whatever I explained makes more sense. You see that this build platform keeps on moving up and down, and simultaneously in the bottom, the light is projecting. Also, one second, yeah. The process is photopolymerization that happens, right? And you will notice that in this vat, the material or the resin which is placed is not in a fluid structure. It's not flowing about, or it's not in the entire surface. So the reason being, you have something called as a PDMS vat. The idea behind using a PDMS vat is actually to first um, allow the allow the transmission of light through that resin bed that you have. Another reason being, we need to take care of the surface tension. As the print bed keeps, or the build platform keeps moving, you'll notice that the fluid will also keep moving. So it makes it hard for all of the material to stably create the structure you want. And having taken care of your surface tension, you can easily be able to get the surface area between the build platform and the resin bed equally. So when you use a photo ink, right, a hydrogel, we know hydrogels are liquids or semi-solid materials which have a specific gelation property. They can retain a lot of water. They have something called a swelling factor. They are good in terms of nutrition. It allows good amount of nutrition for the cells to thrive in. And while they are just hydrogels, they lack the capability of just directly photopolymerizing. They don't just photopolymerize unless you add something to it, right? So you have to make a material smarter and better for it to function in the way you want it to be. So in this process, while we are creating the hydrogels, we are going to use photoinitiators, cross-linkers, basically the cross-linking agent, and then you have the material itself. And following that, right, when you have optimized a material or when you have used a material, you need to take care of, say, the exposure time, the intensity of the light that it is printing in. I cannot let the light intensity be too high when I'm using cells, because this can damage the cells, right? Exposure time again should be adequate. I cannot make it as less than 1 second or less than the standard number of time it will take to cure. Next is obviously the wavelength of the light. Like I mentioned, it's 405 nanometers. So we keep all of these factors in mind while we are creating a hydrogel, in order for it to create the structure and in order to retain the mechanical stability. So with the inks, right, with hydrogel inks, with the photo inks, we have optimized. There are a few which are in making. There is a lot of process happening, a lot of optimization happening, where they have come down to materials like PEGDA, polyethyl glycol diacrylate, right? That is one. And then you have GELMA, which is gelatin methacrylate. These are photo inks, not in their original forms, but in the optimized and the customized forms. They are customized, like I said, to the previous notes, right? So when you're talking about the PEGDA, we have a series of materials that are available in them, and they have been modulated in the factor of it being able to it being able to adjust to different struts. Say example, you have a scaffold and you need a strut of, say, so much micrometers, or you want the distance to be so much, you want the pressure to be so much, so you need to optimize it. So that way we have PEGDA, PEGDA start, PEGDA 500, PEGDA 200. So these are all of different stiffnesses, and obviously they're biocompatible, except PEGDA material is not a biodegradable material as such so easily. It is biocompatible, but not very easily biodegradable, and it has a very different degradation time, because this is a material that is not naturally synthesized. It is a artificially synthesized material, right? And then you have GELMA. So GELMA is rather a natural form of gelatin, and this is supposed to help or allow in better cell growth, and that's why we tend to use GELMA as a photo ink in order to print with cells. So you see in this image that you can easily put the cells, mix the cells along with the photo ink on the print bed resin, and you can print it with the cells. Yes, you will have a difference in the viability of the cells, basically the live dead assays of the cells, and the contamination factors to take care of, right? These are some things you can control for sure. And there is also another factor. You will wonder that, okay, I have a photo ink, maybe of room temperature, and I have my cells which are supposed to be alive at 37 degrees, right? So the print bed, or where the projection happens, also has a feature of taking care of the temperature. So it can heat it up to a point where it can come up to 37 degrees. So the idea is to make it a very comfortable environment for the cells to grow in while they are going through this process of photopolymerization. So the applications are going to align with the applications we have dealt with time for you to understand how better or how differently we can create these models. So you have 3D cell culture. We have talked about how 3D models are more in demand or more efficient in terms of representing humans, representing animals. And then we have the biomaterial development. So this is a very growing area because we have so many materials naturally available that can be easily optimized. I wouldn't say easily, but can be optimized to an extent that they can allow creating your so-called artificial organs. Then comes organ on a chip or microfluidic devices. We have also spoken about microfluidic models and organ on a chips where you create a easy testing platform, or you create a platform in order to allow a better study of microfluidics itself. Then comes complex tissue models. So while we use extrusion printing, we can create, tissue models, and they can be complex. But in case you're looking at creating something a little more intricate, right? You need something of high resolution. That's when DLP bioprinting will come in. So I'll talk about a couple of cases which are in favor of how DLP printing is. So if you know about organogenesis, right? Organogenesis is the process of how the organs are formed in our body. And in this process of forming or growing, right, a person growing, an embryo growing into a fetus, you will know that the heart is the first one to grow, or the heart is the first organ to form. So here, this study is actually for us to understand the development of the heart, right? And this is to understand the cells and the dynamic microenvironments that you would be using. So in this study, they have looked at an embryo heart as well as a fetal heart. So in an embryo heart, they have seen at day 22 and a fetal heart at day 33, right? Week 33. So when you're looking at these, you will see that definitely through these images, they are more developed when you compare them. So the kind of techniques we would use, we would definitely go for imaging. We would go for either ultrasound, or we will go for MRI. So the MRI which is taken is a 4D MRI, which is us considering time also and picture. Time and space are two things we always try to match and try to study and understand. So using these images, right, using these slices, we convert our 2D slices into 3D slices and forming a CAD model, right? And now we already know what form of bioprinter we're using. This is a DLP based bioprinter. So the investigation that you do over here is actually going to be, one, the use of bioprinting itself, and also the perfusion. How is there going to be a flow? We need to check the hemodynamics. We need to see the flow study. We need to also understand the impact, and also we need to know how factors like space, how factors like flow rate can impact the development of a heart, right? So end of the day, we will be using cells here, and we will try to understand that how is the developmental process happening. And if we understand this, or if we are even close to understanding this, maybe this will give us a good understanding of certain diseases. How could we diagnose diseases, or how can we avoid diseases? So these are the main research work that is happening. And here is where we start with this. So when you see with the embryonic heart, you will go with maybe a simple tube, right? The tube formation is the starting process of organogenesis, and then comes the rest of the parts where you have the ventricles forming. And now we are studying the left ventricle as well as the tube, basically the heart tube, right? So once the printing is done, here in this printing we have used 𝗕𝗛𝗚, right? 𝗕𝗛𝗚 ink. So we have eventually seeded with cells. Point being, first we need to analyze what is the flow, how is it affecting the structure that we have created. We have created a model, but we cannot just directly use cells into it, because we need to know and understand what is the impact of a liquid flowing within that structure, because it goes through a lot of shear stress in order to flow through every part, right? So once you have your cells being seeded, we are using endothelial cells. So endothelial cells are the basic unit of the tubes, are blood vessels, right? This is the whole laminal structure. And the nature of HUVECs, which is endothelial cells, is that they have a habit of stacking up line by line, right? Few cells have a nature of forming a flat surface, sticking to a flat area like fibroblasts. Some of them are circular, some of them have a nature of binding to the sides of a wall, right? So they do the study here, and later on, after they have done this cell seeding, they have been able to understand through perfusion studies that which part is getting developed more or which part is affected more, where do you see a better cell viability, and also what is the flow dynamics within the heart. So there are two things here, right? You have an interplay where you're seeing the cell-cell interaction, you're looking at the cell and ECM interaction. Also, you're looking at the spatial factors, you're looking at the flow factors impacting the heart. So this study consists of two major giveaways. Also understanding us or making it so easy for us to create models of heart, while it was something that we couldn't have imagined long ago. So while this has happened, they go through analysis and they understand that, okay, in certain regions, the perfusion is less, so the cell viability could be less. And this kind of leads to creating better study outcomes, and for us to understand, the growth or the progression of the left ventricle and how it could progress, right? Now, if I know if one particular section is not functioning properly, then maybe, okay, the blood flow is a problem, or maybe this is a particular section we need to deal with, right? These are just scenarios that it's quite complex. So this just helps me tell you that you can use in creating such complex hard models very easily. So this is thanks to imaging. You have computational modeling, which is, say, example, softwares like MSc. You have imaging techniques, and then again you have bioprinting. So it's an amalgamation of quite a lot of technologies being put together to actually create these research outcomes. So this is another one, and this is a slightly complex case. This is creating a thermofluidic pattern or a thermofluidic chamber for gene patterning. Here they are trying to study the heat exchangers for actuation of transcription. So this is more related to genetics and also trying to see what impact cells would have, right? They want to see how hypo or hyperthermia can impact the effect of genetic regulation of the cells, right? This is the whole study. And here we started with using or creating a single fluidic channel, and they started to see the impact, right? A flow which is happening through convention and transduction methods. So the temperature is also something which is monitored and seen over time, and over that you have flow analysis that is happening. So initially, as usual, it is going to start with without cells, then you go with cells, then you analyze as the temperature increases, what is the impact, right? What is the impact on the irradiation? What is the impact on the genetic expression? So this progresses over trying it in vivo over a rat model, where they now try to go with complex fluidic structures. So instead of one line, maybe it's a cross, right? Or maybe it's a little more complex. So with each complexity, they were able to understand, because why the complexity is created in the first place, right? Why are we testing it with complex models is because that's how our blood flow, our veins, our nerves are, right? They are not in a specific pattern. they're very irregular, and there is quite some fluidic flow, and we need to analyze that. So while I told you of two cases, the potential is very high in DLP bioprinting. No doubt, extrusion printing is an amazing technique. It's also a technique which is widely used, and it's more easier to use. DLP printing on another hand is more of a complementary technology to extrusion printing itself. So the potential of DLP printing is one, the biomaterial development. So you can create so many natural polymers. You can really mix and match and see that you can use biocompatible materials, more mechanically strong materials. And as these materials are developed, you will eventually use them in creating models, in creating maybe tissue models, disease models, etc. So, while DLP is a technique which can work with or without cells, it creates a better medical device manufacturing, right? Because you will be combining tough materials maybe along with natural materials, understanding whether this is the most biocompatible form. Because the main thing about medical devices is that they have to be biocompatible, right? So having a printer which easily can take care of the exposure times, taking care of the light intensities while you're optimizing the material, will help you create maybe functionalized devices or implants. So anatomy models, like the previous case we saw with the heart, we could easily create such a delicate structure, maybe in a smaller scale, but enough for us to understand the disease. You can create disease progression models. You can have pre-surgical models as well. So pre-surgical models are basically when there is a complicated case, and a surgeon needs to take care of the surgery. And before taking a surgery, the best way is to understand the body of that person. So we are all unique creatures. While we are all humans, we are all quite unique with our structures, our anatomies are different. And so there is a need to incorporate imaging techniques and also 3D printing techniques. So you can use this pre-surgical modeling for either by using bioprinters or normal plastic printers for you to understand what is the right way to access a particular point of surgery. Say example as a tumor, say example as something you need to remove. There's an extraction process that needs to happen. So you can plan it easily, so that what this actually does, right? This planning can, one thing, reduce the amount of comorbidity. You will not have to suture through multiple places to get to that site. So there is something called cutting guides where we use. Then we have another area where you can save, that is time, and obviously you will save money. So these are some very interesting applications where you can potentially use DLP bioprinting. Then you have in vivo implants, right? So biodegradable materials using natural hydrogels or maybe resins, you will be able to create very simple structures. So if you talk about a nerve conduit with channels, right, you can easily create channels while you can create a tube. I know it sounds just like a tube, but creating a tube is a lot of work. You need to understand that when you are stacking a structure in the z axis, you need to say that till a certain point there has to remain a stability of the structure, while you also make sure that it is photocured, right? Mechanical stability as well as the complexity of the structure and why I'm creating the structure is quite important. Then you can obviously create customized materials, customized models. For example, here they've used customized zirconia implants. This is one of the potential places, and here I'm just showing you some examples. Say there they've tried to create maybe a hard bone, a soft muscle structure. So you can easily create this sort of structure. Then you have maybe the dental area, the dental implants, surgical guides, maybe any other form of your head or any other part of your body, right? Then you have filling materials. So hydrogels, like I told you, are biocompatible. They are good in aiding treatment, in wound healing and other forms. So you can use this as a filling material. And now the question is, okay, why can't I just put the filling material directly? No, the incision that is made is different. The size of the incision is also going to matter. If I can create something like a graft which is of customized nature for a patient, then I will be able to efficiently create these or set the results for that. Then you have drug delivery systems and drug discovery. So drug delivery systems would be maybe a microneedle, like I mentioned in the previous session. You can easily create the the incision points or how these needles points are with DLP printing. You have drug discovery, that is again through organ on a chip, maybe 3D cell models or tissue engineering models. All of these are made quicker. And then you have microfluidic studies. So there's a lot of microfluidic studies, a lot of analysis that is being done, and you need quick forms or quick, easily perfusible forms of channels that you can create to carry out the study. So if you see this model here, it's a complex loop, which is a circle, and around it is a continuous loop. So creating a structure like that can also be easily done when you use DLP based printing. So again, I'm going to play this demonstration video, which will give you a proper flow of everything. So here you start with the calibration process. So every machine needs a calibration. So we go through a calibration just to make sure that the build platform is intact with the resin bed. This is to improve the surface contact, right? Then you see there is a exposure time, light intensity that you can adapt and adjust based on material. Here they put the ink. So with this ink, you don't have to entirely pour in the material that you want. The machine itself is going to tell you, okay, for a 3D slice or a structure of this dimension, this is the amount of photo ink you will require. So you can conveniently use that to avoid any sort of wastage. So this moves as the light is passing through it, and as it passes through, it would create a model like this. So that's with the Luminex, which is a DLP based printer. And you know about our other solutions, which is Incredible Plus, BioX, BioX6, BioMDX. Telling about BioMDX, it's actually an industrial grade machine with multiple set of print heads, liquid handling, high throughput screening, and other functions. And then we have Luminex. So in our life sciences solutions, we also have BioVia, which is a biological modeling simulation suite, and it has the BioVia Discovery Studio, and this completely works with bioinformatics and cheminformatics solutions. So here you can just shortline the time to discover a drug or go through that process of creating a pharmaceutical product. So this is the quiz question, and the question is, which technology is digital light processing related to? Filament extrusion, SLA, inkjet, SAF. So you can scan this to visit our Altem page, or you can simultaneously visit Altem Technologies on LinkedIn or other platforms where you can answer this question. Also a reminder, the person who will win this is going to be someone who has correctly answered all of the previous questions, including this. So thank you so much. Thank you for sitting through the session, and thank you for attending all the previous sessions for who attended it. And kindly subscribe, share, follow us as much as possible, and please pass this word, because since we're not only a life science solution platform, we provide you solutions with everything and anything possible, so you can easily contact us. Yeah, thank you. This is the end of the session.
All right. So how was the session, guys? Did you like it? Yes. Wonderful. I'm sure you all enjoyed this knowledgeful session, this empowering session, this enriching session. And now that we have come to the end of our power-packed series of bioprinting, now is the time to give you the goodies and the e-certificates. So we're giving the link in the description in the chat box right now. Please fill the form. Please fill it very, very carefully. Make sure that the email IDs are correct. And followed by that, in the next 7 working days, you're going to get your e-certificate. Okay, it will be emailed to you. If in case you don't get it, please contact us. Okay, you know how to contact us. You can email us at info@biotechnika.org. And in the meanwhile, the experts of Altem will confirm us on the Q&A session if we can have a special Q&A session, so that we can have that session also, and where you can ask your questions and all your doubts and queries can be answered, right? So with this, we come to an end of our 6 sessions. You know, guys, all good things come to an end, but I believe this is not the end. This is the beginning of your excellent research career in bioprinting. I believe this is the beginning of your odyssey, your journey, where you can utilize this excellent tool in your research. And that's all for now. See you in our next webinar. Thank you so much for watching. Bye-bye. Take care.